In the last video, we discovered an astounding relationship between pi and probability. If you take hardwood floor, or any large surface with evenly spaced lines, then cut a skewer to be exactly the length between two lines, and toss that skewer so that it lands randomly on the surface, the probability of the skewer crossing a line is exactly 2 over pi. Pretty cool, but why does pi show up here? At the end of the video, I left you with a little thought experiment to get started on this problem. Let's say a kind wizard comes by and gifts us with a magical skewer. What makes this skewer magical is that no matter how we toss it, it will always land perpendicular to the lines on the surface. Obviously, the probability of this magical skewer crossing is no longer 2 over pi. But what is it? Well, let's toss it a bunch of times and see what happens. Interesting. No matter where the skewer lands, it always seems to cross a line. But isn't that what we'd expect? The skewer fits exactly between two lines, meaning as soon as it stops crossing one line, it begins to cross the next. So, the magical skewer will cross 100% of the time, corresponding to a probability of 1. Now what if instead we encounter an evil wizard who gives us a cursed skewer? Under this curse, the skewer can only ever land parallel to the lines. How does the probability of it crossing change? Well, let's try tossing the cursed skewer a bunch of times. Whoa, none of them crossed. But again, isn't that what we'd expect? Unless the skewer lands directly on top of a line, there's no way it can cross. And even in this case, we're going to be overly idealistic and pretend that the skewer and the line are extremely thin. So the probability of the cursed skewer crossing is essentially 0. Let's take these results and graph them. On the vertical axis, we'll put the probability of the skewer crossing a line. And on the horizontal axis, we'll put the angle the skewer makes with the lines. Landing perpendicular corresponds to an angle of 90 degrees. So if a skewer lands at 90 degrees, the probability is 1. On the other hand, landing parallel corresponds to an angle of 0 degrees. So if a skewer lands at 0 degrees, it has 0 chance of crossing. But what if the skewer lands neither perpendicular nor parallel, but somewhere in between? If we had a magical skewer that always landed at, say, 45 degrees or 60 degrees, what would its probability of crossing be? To figure this out, let's determine the probability of the skewer crossing as a function of the angle theta it makes with the lines. When the skewer lands at an angle, we can think of it as actually being two smaller component skewers. One of these components is parallel to the lines, and the other one is perpendicular. These component skewers each have their own probability of crossing, and the probability of the original skewer crossing is just the sum of these component probabilities. From earlier though, we know that the probability of the parallel component crossing is 0. So the overall probability is just the probability for the perpendicular component. Remember how we determined that the reason for the magical skewer always crossing was that it fit perfectly between two lines? Well, this isn't true for the component skewer, but we can use the same logic to figure out what its chance of crossing is. Let's say that the perpendicular component happens to be half of the distance between two lines. This highlighted region represents where the middle of the component can land in order to cross a line. When it's inside, the component crosses, and when it's outside, it does not. Notice how this region takes up exactly half the surface. This means the component will land in it half the time, and therefore its probability of crossing is 1/2. Interesting. it seems the probability of the component crossing is the same as the fraction representing its length. And this is actually true for any length of the perpendicular component. If it's 1/3 of the line separation, it'll cross 1/3 of the time. If it's 1/4 the separation, it'll cross 1/4 of the time, and so on. If we call the distance between lines L, and the length of the perpendicular component x, that means its probability of crossing is x over L. Then the overall probability of the skewer crossing is also x over L. Let's call the angle the skewer makes with the parallel component theta. This angle is the same as the one the skewer makes with the lines. For a right triangle, sine theta is the ratio of the opposite side to the hypotenuse. Here, the opposite side has length x. The hypotenuse is the full length of our skewer. If the skewer fits perfectly between two lines, however, this length must be L. Since p and sine theta both equal x over L, then they must be equal to each other. So, the probability of the skewer crossing a line, as a function of the angle theta it makes with the lines, is just sine theta. Now that we know p equals sine theta, let's put it onto our graph. We're almost at the final step, but there's one small change we need to make first. Right now the angle axis is in units of degrees. Degrees are great for visualizing angles in real life, but they don't always work when doing math. For our final calculation, we're going to need to think about these angles in their natural units of radians. If you've never seen radians before, wrapping your head around them will take some time, but the underlying principle is pretty simple. Consider a circle. If you were to walk all the way around that circle's circumference, you would have gone a full 360 degrees. A circle's circumference is just 2 pi times its radius though. So instead of calling the angle 360 degrees, we can call it 2 pi radians. If 360 degrees is an angle of 2 pi, then 90 degrees must be an angle of pi over 2. And that fraction seems familiar, doesn't it? Let's not get ahead of ourselves though, there's still one more step to reach our final answer. This graph shows the probability of the skewer crossing at every possible angle it could land. And if the skewer was tossed randomly, each of these angles is equally likely to happen. So the overall probability of crossing is just the average value of this graph. Finding the average value of a graph is no different from, say, finding the average height of a hill. In fact, to make visualizing this problem easier, let's pretend that's actually what we're doing. This hill spans a distance of pi over 2, and has a height between 0 and 1. To find its average height, all we need to do is take the area under the hill and divide it by its length. Length is the easy part. That's just pi over 2. Finding the area, however, will take a bit of thinking. The hill is shaped sort of strangely. It's not like we can just multiply a couple of numbers to get its area. But what's an easy shape we can do that for? Rectangles, of course. So, let's approximate the shape of our hill with a few rectangles. We can now calculate the area of each individual rectangle. Adding up these areas gives 1.006, which is an estimate for the area under the hill. Cool. We can do better though. Let's add more rectangles to get closer. With 7, the total area is now 1.002. There seems to be a pattern here. As we add more rectangles, the total area gets closer to 1. And indeed, if you were to use infinitely many rectangles, the resulting area would be exactly 1. If you've got a bit of calculus under your belt, you probably recognize this as being the integral of sine theta. Evaluated from 0 to pi over 2, which is just 1. If not though, that's okay. We've got our area, we've got our length, and by now you can probably see our final answer. 1 divided by pi over 2 gives us 2 over pi, which is the average height of our hypothetical hill, but also the average value of our probability graph. So there you have it. That's how we can show that the probability of the skewer crossing a line is 2 over pi. I hope you enjoyed this video and that maybe it sparked your curiosity a bit. Some of the math I used here wasn't super rigorous, but hopefully it made for a more intuitive route to the solution. If you're interested in learning more, look up Buffin's needle problem. This experiment was actually first proposed by an 18th century French mathematician. Since then, it's been thoroughly explored, and there's lots of other cool information out there about it.